Neurons send signals by generating and changing electric potentials across the plasma membrane. How? Turns out it's all about ions. To understand what happens in neuron signaling, let's first consider how ions that cross cell membranes create these electrical potentials. To cross the cell membrane, ions use membrane proteins called ion channels and ion pumps. First, we'll talk about ion channels, which are passive diffusion mechanisms. They can be leakage channels, which are always open, or gated channels, which are open when stimulated. Some ion channels match specific ions. There are sodium ion channels and potassium ion channels, for instance. The outside of the neuron cell acts as the positive pole, and the inside of the cell is the negative pole. When opposite electric charges are separated, we have potential energy. So, the two poles inside and outside the cell create an electrical potential across the cell membrane that measures at an average of negative 70 millivolts. Thanks to the cell's sodium-potassium pump, there is a higher concentration of potassium in the cytoplasm in the cell and a lower concentration of sodium. Outside of the cell, the concentration of sodium is higher and potassium is lower. This imbalance leads to the diffusion of potassium ions through leakage channels in the membrane. But the membrane is not permeable for the negatively charged phosphates, proteins, and nucleic acids inside the cell. So, a negative charge builds up in the cell and a positive charge builds up outside the membrane. The negative charge then pulls the potassium ions back inside the cell. A small amount of sodium is pulled in as well. The energy resulting from the balance of diffusional and electrical forces, the equilibrium potential, can be calculated by the Nernst equation. For a single potassium ion in the cell membrane, this equation would be equilibrium potential is equal to 58 millivolts multiplied by the log of the sum of K concentration out divided by log K concentration in. The result for potassium's equilibrium potential is negative 90 millivolts, but the few sodium ions that leak into the cell decrease the magnitude of the potential to negative 70 millivolts in the neuron, which is in accordance with real measurements. Neurons are unusual among cells for the way that their membrane potential can change abruptly from their resting state in response to stimuli. Changes can be graded potentials, small and gradual, or they can be action potentials, sudden and brief. We've already mentioned gated channels, unlike leakage channels, which are always open. Gated channels only open in response to stimuli. Think of them as doors that you can open and close. One type of gated channels, called ligand-gated channels, open for chemical signals like neurotransmitters and create graded potentials by altering membrane permeability to ions. When a potential becomes more positive, it's called depolarization. When it becomes more negative, it's hyperpolarization. The second type of channels, voltage-gated channels, respond to changes in membrane potential, and they create action potentials. Action potentials are the signals that travel through the axon. How does that whole process work? When a sufficiently large excitatory stimulus, called a threshold stimulus, reaches the cell, ligand-gated sodium channels open up. Then, when the threshold potential of negative 55 millivolts is attained, voltage-gated channels for sodium ions open. Sodium ions rush into the cell, causing depolarization, and an action potential is created. These action potentials are then sent along axons. The sodium channels shut and the voltage-gated potassium channels open. Potassium diffuses out of the cell, causing repolarization and then slight hyperpolarization, which is increased negative charge inside the cell. Finally, the gated channels shut and the cell returns to resting potential. It may sound complicated, but these changes in electric potential are at the root of all neuronal signaling and everything you do or think.